For a linear algebra problem, I wrote down 3 random vectors from R3, and I was saying most likely that means it's going to be a basis of R3. And the goal is to explain why. Explain why B is a basis, you could say, of R3 or for R3. 2 conditions to be a basis. It's got to be a linearly independent set. And it also has to span whatever you're saying it's a basis for. If I only had 2 vectors here instead of 3, 2 3-dimensional vectors that are not scalar multiples of each other, they would be linearly independent, but they would not span R3. They would span a plane through the origin, though, a subspace of R3. They would be a basis for a certain plane, whatever plane they lie in through the origin, when you draw them so that the tail is at the origin. So you always need to say, when you're saying something's a basis, what is it a basis for? In this case, all of R3, or again, if I was just looking at 2 of these, it would be a basis for a certain plane. Planes through the origin are subspaces. They are vector spaces in their own right. They are closed under addition and scalar multiplication. But I am talking about R3 here. I've got 3 vectors. Well, first, linear dependence. Let's give these vectors names, v1, v2, and v3. To truly explain this, to truly prove this, you need to give an argument. Am I really looking for a full proof? Well, probably not. I didn't say proof. I did say show, but I'm after a basic explanation with some words. Really, we need to assume x1 times v1 plus x2 times v2 plus x3 times v3 equals the 0 vector. I almost started to put a little, oh, I did put one above that one. Okay, there's the x's are scalars, the v's are vectors. That's why it's a good idea to use little arrows above things to emphasize what's a vector and what's a scalar, if nothing else for yourself conceptually, so you don't misunderstand. Okay. When mathematicians prove things, they always often speak in the third person because they're trying to bring people into what they're saying. So they say things like, we must show x1 equals x2 equals x3 equals 0. That's the 0 vector. This is the number 0. Well, things like this without writing some words are equivalent to systems of equations. First equation is going to be x1 times 1 plus x2 times 2, which is 2x2, plus x3 times -4, minus 4x3 equals the first component of the 0 vector, which is 0. Then for the second equation, you use the second components, 4, -3, and 1. 4, -3, and 1. Am I doing a bit of overkill here? Yeah, probably, but just for your sake, I'm trying to emphasize what's really going on in writing the system of equations out. If we solve this system, this homogeneous system, that's worth emphasizing, by row reduction, and so, yeah, somebody was asking about this. Row reduction is sometimes called Gaussian elimination. Okay, I'm going to go ahead and write an augmented matrix here. We also say we get. If you did this without an augmented matrix, it's okay. But the non-augmented part, the part to the left of the dashed line, ends up being the identity matrix when you row reduce. And it's fine if you want to use technology there now from now on. This part has a pivot in every column. I mean, there's no pivot in that column, but that's the augmented part. That's the right-hand sides. I can ignore that. And that's why you can just focus on the original matrix and not write an augmented one. There's a pivot in every column. There's no free variables. X1 must be 1, X2 must be, X1 must be 0, X2 must be 0, and X3 must be 0. Therefore, X1 equals X2 equals X3 equals 0. And that's enough to prove that those original vectors are linearly independent. Am I looking for quite so much in your homework? Not necessarily. You don't have to rewrite the system. You could say, I'm just going to row reduce the coefficient matrix and see that I get the identity matrix. Although if we just had 2 vectors instead of 3, we wouldn't get the identity matrix, but we would get a matrix under row reduction that still has a pivot in every column. So the corresponding homogeneous system would still have no free variables. And the x's would still be 0. What about spanning? In other words, i.e., is R3 equal to the span of V1, V2, V3? That's just special notation. Whenever you see span of a collection of vectors, that's really an infinite set. This collection of vectors is not infinite, it's finite. There's just 3 vectors in it. But when I put the word span in front of it, that's just shorthand symbolism to represent a certain infinite set, the set of all linear combinations of these things, as the weights vary over all real numbers. So there's infinitely many things in such a span, unless all these happen to be the 0 vector. How do you prove that they span? It ends up being equivalent to there being a pivot in every row. Being linearly independent is equivalent to there being a pivot in every column of the row reduction. Being spanning means there's a pivot in every row. And it would be good enough for your assignment if you just say that. Hey, I row reduced the coefficient matrix. I got the identity matrix that's got a pivot in every row. If you were really looking for a fuller proof, you'd want to do a more general REF. I'm not going to write any explanations here for sake of time. If you're really after a more full proof, you'd want to show that you can solve a general system of equations where I have arbitrary numbers A, B, and C there. But what's going to happen when you do your REF in this situation is the first part will be the identity matrix. And you'll get some possibly complicated stuff over there involving A, B, and C. But because you got a pivot in every row, you will be able to solve for X1, X2, and X3. X1 will be something, X2 will be something, X3 will be something involving A, B, and C in each case. The system is consistent, it's solvable. And that's enough to prove spanning, because what you've really done there is you've really given any vector A, B, C in 3-dimensional space. This process tells you how to find I went to second person there instead of third person. Tells us how to find scalars x1, x2, and x3 such that x1 v1 plus x2 v2 plus x3 v3 equals this vector ABC. And the formulas for x1, x2, and x3, these scalars will involve A, B, and C. You can find formulas for them. It ends up being equivalent to inverting a matrix, actually, and you get fractional formulas typically. And in finding the coordinate vector for the vector I showed you, which was this one, we are effectively doing that. That's like my A, B, and C. To find the coordinate vector for a given vector means using this is your original vector. When you do the solving and find these numbers, those numbers are the x's. If you put them in a three-dimensional vector, they end up being the coordinate vector that you're after. So let's go ahead and use Mathematica to do that. So here you really do want an augmented matrix. It's fine if you use your calculator. So the coefficient matrix is in the first three columns. My x vector is in the augmented part to the right of the dashed line when you draw it by hand. I typed all that. I was comparing it to the original problem here. V1, V2, and V3 are the first three columns. Make sure I type everything right. And the X that I'm after, that's like the A, B, and C I was just writing at the bottom of the page. That's the last column. If you draw it by hand, you'd put a dashed line before that. When we row reduce, the first three columns we already know are going to row reduce the identity matrix. These last three are what X1, X2, and X3 are. So what you would write, kind of funny notation, you'd write that the coordinate vector of X with respect to B, what we're trying to emphasize here is it's going to be a vector. It doesn't actually equal the original X in ordinary Cartesian coordinates. But with respect to some slanted coordinate system where we've slanted the axes in three-dimensional space in some way that I'm not drawing, and had some sort of slanted three-dimensional graph paper, it would be the coordinates, if you can imagine such a thing. I'm literally saying, trying to imagine three-dimensional space with slanted coordinate axes that result in three-dimensional graph, quote-unquote, paper, not really paper. The numbers here, 10, oh, I can write these as decimals nicely, 14.3 and 8.9. Those numbers would represent the original vector in the new coordinate system. I did row reduction to solve for that. We can also use matrices and inverse matrices. And that comes up in the lectures too, something called the change of coordinates matrix. And all that's related to change of coordinates, which is related to the skew coordinates, like with the differential equation system that I did with the eigenvectors, defining a new coordinate system that's skewed, in which we can solve the system more easily, and ultimately even compute the matrix exponential by hand. But there's still a fair amount of work to do.